Okay, so let's start. So we have 19th lecture today for this course, Advanced Electric Drives, and we have seen the different PWMs so far, which is like selective harmonic elimination and then the optimized pulse width modulation. What are those and what we are trying to achieve? So we saw that basically when we have enough degree of freedom, we can eliminate the dominant harmonics. So let's say we have two switching angles per quarter, which means 2 degrees of freedom we have. So two independent equations can be solved, and which is what is shown over here as well, and keeping the inequality condition there. So this is for two switching angle, but it can be extended for any general n switching angle case. And what we are basically finding that by doing so, we are following one of this V5 equal to 0 curves, either this or this over here. Now, since we have multiple options, so we may look for, when we have already eliminated V5, which is the next most dominant harmonic, so which is V7. Now we can look for the option which is giving me lower value of V7. So obviously this seems to be a better option. But we have seen some problems with SHE PWM. For example, the solution is not available completely. First of all, it has multiple solutions. So we need a second parameter to decide which one to choose. Then solutions are not available for complete range. So particularly for higher modulation index, the solutions are not available. And then if we are trying to eliminate, sometimes the another harmonic may become very high. So seeing all these difficulties, we have gone to better methods. Let's say we do not eliminate any harmonic, but we take set of harmonics and minimize that, say 5th and 7th. So we try to minimize that. So somewhere, if you seen the contours in the alpha 1, alpha 2 plane, so this path in between V7 and V5 equal to 0 could be a good place. Or maybe after this point, it may shift on the other side of the graph here. So because we are picking up the point based on the minimum value, so it will have a solution and it will have unique solution. So the problems associated with SHE are no more there. We have unique solution and the solution is available for complete range of modulation index. And we can choose whatever number of harmonics we want over here. Now we are finding that we are giving equal weightage to all the harmonics when we are doing such arrangement. So somebody may point out that why so? Because the lower order harmonics are more dominant, are more important. We should look for that. And actually, it is the current which we are concerned about and not the voltage. So directly we can have something like this getting minimized. Some of all the harmonic currents getting minimized and other conditions are there as it is. So better way to say is that we are trying to have the total harmonic distortion in line current minimized. So the total harmonic distortion in line current is basically sum of all the harmonics and then divided by the fundamental. So from here what we are seeing that there is dependency for both the quantities on load. So then if we are solving for one load and we change the load for, let's say we go connect to another load, no, then the solution must be different. So we need something which is independent of load. So this is where we come with the expression for the harmonic currents in terms of the harmonic voltage, because harmonic voltage is only based on the PWM voltage. It is not dependent on load. So what we have basically is that this parameter In can be replaced by something like Vn by N when you take out 1 by omega LL outside. So now here we do not have any current component in the numerator. Whatever quantity Vn is there, this is fixed. Once you have fixed PWM pattern, let us say 2 switching angle, the harmonic is fixed. 1 by n times of 1 minus 2 cos n alpha 1 plus 2 cos n alpha 2. Or you can extend it for any number of switching angles. So once the PWM is fixed, this is fixed. Now we can find the minimum value of this numerator. But still, there is some dependency for this fundamental current on load. So what we can look for? We can look for the worst case fundamental current. And in case of induction motor, the worst case fundamental current is basically our magnetizing current. So magnetizing current can be written as approximately in this form. And then what we are finding that our total harmonic distortion in line current is coming proportional to another quantity which can be called as weighted THD of voltage. So because every harmonic is weighted with respect to its harmonic order over here. That's why this is called weighted THD. And this makes sense because lower order will have more weightage and higher order will have lesser weightage. So if you talk about fifth, it will be 1 by 5, whereas seventh will be 1 by 7, 11th will be 1 by 11, and so on. So we are giving more importance to lower order and lesser importance to higher order. Now, this weighted THD of voltage could be a universal quantity and it is related to worst case THD. Again, I am repeating this term worst case THD, ITHD, because we are taking the least value of fundamental component, which is basically the magnetizing current. If you take at any load value or full load value, the value of ITHD will only be better than whatever you get. So we have no problem with that, right? Clear, right? Any problem in this?
No, sir.
Good. So we have found our parameter ITHD in terms of another parameter V weighted THD, which is only dependent on the PWM voltage. There is no dependency on load. So all the harmonics in or all the components in this can be defined in terms of the switching angles. So a better optimized PWM can be, a more general optimized PWM can be, you minimize the weighted THD of voltage, and particularly I am concerned about the harmonics which are present in the line to line voltage or line to neutral voltage, which means the harmonics considered here are 5th, 7th, 11th, 13th, 17th, 19th and so on. Because the triplet harmonics are cancelled. So we need not worry about those. Even if that is high, it will get cancelled. So which is how this can be minimized, and keeping these constraints in mind. So if we have n switching angles, this could be a general constraint available for this minimization problem or optimization problem. Understanding my point?
Yes, sir.
Clear?
Yes, sir.
Okay. So now let's move ahead. Because we are dealing with motor. So far what we are doing, we are trying to have better value of line current. But when we are dealing with motor, there is another quantity which is very, very important and which should be of concern for any power electronic engineer, and which is torque. Isn't it? This is what is our ultimate output. Current is only giving this output, right? So somebody may suggest that why not we minimize if there is any ripple or on the torque or any particular torque harmonic. Why can't we do that directly instead of getting stuck in the current and other things? This is also possible, right? Fine? Yes or no?
Yes, sir. Yes, sir. Yes, sir.
Then first we need to understand what is the relation between the torque harmonic and current harmonic or any other quantity. So which means how a torque harmonic is generated in system. How it is generated. What causes this torque harmonic in the motor, and particularly I am talking about induction motor. So one analysis we can do based on induction motor, and similar things can be extended for other motors as well. So today we will see how this is generated in induction motor. So we'll go back again to our equivalent circuit. That is very, very important circuit, although it's very simple, but it gives lot of information about our motor and the current and torque what is going to be generated in the system. So Okay. So what is general understanding about torque? What is torque? See, one way we have derived from the equivalent circuit, what we have done, we have computed the output power and then we have generated. So P mechanical divided by omega mechanical, and this we have said as the torque. Correct? This is what we have done, right?
Yes, sir.
Now, the question is, this is not the cause. This is only the output what is coming over there, right? We are only equating the power with torque into omega and we are getting our expression. But what is the more basic rule or more basic way of developing a torque in motor? How a torque is developed in motor?
Because of the interaction of the fluxes, the rotor and the stator fluxes.
Okay, interaction of flux. Now, which flux you are talking about?
Sir, both of them actually.
Both means what? You have to be specific.
Actually, the rotor flux and the stator flux, both of them will cause some resultant air gap flux, and because of that, it will create a.
Okay. Now let us go a little more fundamental, because interaction of two flux means both the quantities are kind of imaginary. You cannot measure flux directly, right? You may have only indirect way to measure this. Now let us go a little bit more, no, which is physical. So when you have current flowing in any conductor, let's say I, and it is kept in environment where there is psi flux over there. For example, in DC motor, we have field and we have the armature current. Then what is the torque for this? We say that it is proportional to the flux and the current cross product. So there is flux vector and there is current vector. These both are interacting and generating the torque. So magnitude of torque is basically proportional to the cross product of the flux and the current. This point is clear, right? Any doubt in this? This is the fundamental thing, right? And this is what we will use to derive any other thing in our system. We have already derived the fundamental torque from this expression. And you can go by this method and you can get whether it is matching here or not. So what we have basically, now when we are saying that flux and current, which flux we are talking about and which current we are talking about. So obviously the flux what I am referring to is basically air gap flux. So indicated by psi m, or you can call as the magnetizing flux. And the current which I am referring to is the rotor current, the current which is flowing in the rotor bars. This is the quantity which is responsible for generation of torque in induction motor. Understanding my point? Now we need to see how this flux is generated, how current is generated, and how they are oriented in phasor form for a general nth harmonic or fundamental component. So we know the equivalent circuit of induction motor is something like this. RS and this is LM, let us say. So you are applying some voltage over here. Now, if I ask you, where is the flux generated? Where is the air gap flux generated? Which component is responsible for that? Which component is responsible?
Sir, LM.
LM. So the flux is generated in this LM, or the magnetizing branch is responsible for the torque generating component. Okay, the other components are leakage. Leakage means which is not used. It's some kind of, no, this is getting lost somewhere. We are not able to utilize this. Now, then there is rotor current. Now, which component is responsible for generating rotor current? Which component is responsible for generating rotor current? So there is some EMF, right? Yes or no? Say something.
Yes, sir.
Yes, sir.
Yes, sir.
Now, see here when you draw the equivalent circuit in this form, you are not getting the clearer picture of why we are drawing flux here and then the back EMF here and then the current here and then another voltage over here and then the stator coming something like this. There is no idea coming from this, right? So we have to go a little bit more basic of what is happening in the induction motor. Why we are drawing the phasor like this? Why we have E and then minus E coming over here? What's the reason? So we know that in induction motor also we have the transformer action happening over there for generation of EMF on the rotor side. So what we have basically, let's say if I take out the magnetizing branch separately and have an ideal transformer over here. So we have to look for the cause and effect. What is the cause and it is giving what effect? Correct? For example, if flux has to be generated in the magnetizing branch, what it needs voltage. If voltage has to be generated on the secondary side, what it needs flux. And then if current is to be generated in the rotor side, it needs EMF. So that is how these quantities are generating each other. This is the effect, this is the cause. This is the effect, this is the cause. This is the effect, this is the cause. You understand my point?
Yes, sir.
Do you understand this point?
Yes, sir.
Yes, sir.
Now, when
Yes,
you
sir.
are applying a voltage, let's say this is transformer, don't worry about induction motor and turn ratio and all that, don't worry about all that. Say it is 1:1. Now, when you are applying voltage, what will happen? You will apply basically some voltage across this magnetizing branch. Let's say I call this ES. So what is basically ES? ES is, if you apply KVL over here, it will be VS minus ISRS, and all I am drawing in vector form. L dis by dt equal to ES. Correct? This is what is the voltage which is actually applied across the magnetizing branch. You understand my point here?
Yes, sir.
Yes, sir.
Now, when you apply any voltage across an inductor, what will happen? The flux will be generated, and what is basically flux? It is integral of the voltage, say this, over the time 0 to t. This is M. Any doubt in this? This is the straightforward thing, right? We are only taking the fundamental things. So we have applied ES voltage across the magnetizing branch effectively because the drop in this is subtracted from the supply, and we have generated the flux, which means the flux and ES are going to be in quadrature because there is integral involved, right? And psi m is going to lag ES by pi by 2 because of the integrator action. Any problem in this? Yes or no?
No, sir.
Fine, right?
Yes, sir.
Yes, sir.
This point is clear. We have
Yes.
generated flux. Now let us go for the EMF. So I will call that EMF, which is actually coming on this side of the rotor, on this side of the transformer, you can say. I will call this as ER. Okay, what we have applied here is ES. I will call this as ER. So when there is flux psi m flowing in the system, what is the EMF generated? What is the EMF?
N into d phi by dt.
Why you are taking so much time in this simple question? Which law is this?
Lenz's law.
Lens law.
Lenses.
Is this Lenz's law?
Had his law.
Your all basics are shaken completely. Okay. Now, this voltage is generated because of the magnetizing flux. And which is this voltage? ER. Any doubt in this? Any problem in this? Any problem? Say yes or no. Now, because this is minus d psi m by dt, then ER will basically lag psi m by pi by 2. Fine. Any problem in this? See, so far, I think even the phasor diagram is not understood very properly, right? So today we are trying to understand that. Okay. So we have generated the voltage on the rotor side or on the secondary of the transformer. Now, what is the current flowing in this? Simply ER by Z, right? Correct. So IR will lag ER by some power factor angle, and which is governed by tan inverse of RR by S divided by omega LLS. Sorry, LLR here. Fine, right? Any problem in this?
No, sir.
Clear?
No, sir.
So, okay. Now, this is what we have understood for the fundamental component. So then we can draw the phasor. What we have basically, let us start from the flux, because this is what we know as no common way of drawing the phasor. This is psi m. Now what we have seen that this is positive sequence, which means this is rotating in the counterclockwise direction with the speed omega s. So where is my ES? ES is basically leading psi m because psi m is result of ES. So ES is here. So ES has basically generated psi m, and then psi m has generated ER. ER is lagging psi m by 90 degree. Getting my point?
Yes, sir.
And then what you have is basically your IR, which is coming at some angle, which I have just said over here, with respect to ER. And most of the time, if you see, the slip value will be very small, right? So this will be very, very close to 0 degree. So many a times the rotor current will be very close to, almost in phase with the ER. So somewhere here it will be almost. This is very, very close to 0. This is how we draw our phasor, right? Then we have the IM and we have the IR, these two generating IS, and this becomes our VS. Correct?
Yes, sir.
Fine, right?
Yes, sir.
Yes,
So you
sir.
understood the phasor diagram for fundamental component?
Yes, sir.
Why do we
Yes.
draw like this? So sometimes if you read some good books, you will find the equivalent circuit drawn like the current direction will be shown like this, IS here and IR in this side going towards the magnetizing, and IM here. So they will write IM is equal to IS plus IR. Reason is this, because current direction is reversed with respect to this voltage, ES, what you have applied. Now this is coming because of minus ES. So that's why many a times people who have better understanding, they will draw like this. But there is no problem, even if you draw IR going out towards the rotor resistance, there is no problem, absolutely. As long as you are dealing with the normal circuit. When it comes to phasor, this is where this picture becomes clear. Why we are drawing this IR going towards the magnetizing branch. Fine, this fundamental component is understood. Now,
Sir,
Sir,
why IM is equal to, sir, can you please repeat the point?
Why IM KCL you cannot apply?
Why there is addition?
Yeah, so what else will be there at this point? Both the currents are coming in, this is going out.
Sir, why IR is coming in?
That's what I told. Sampal, you need to listen carefully.
Yes, sir. I don't hear it properly.
You understood this point, ES and ER?
Yes, sir. Okay, sir. Clear, sir.
Correct? Now,
Yes.
because we are showing only one voltage over here, which is ES, so with respect to this, it should be negative in phase. No? So listen carefully. Now, everything, whatever I have told so far for the fundamental component is true, except, so we have same way, even if you take any nth harmonic component, still the flux generation will be true. Whenever you apply some voltage across the magnetizing branch, there will be some flux associated, maybe a small value, but it will be there. And this relation will still be true. There is no problem in that. Psi m lags ES by pi by 2. This is always true. Then whenever we have flux, there is EMF generated with respect to that. So ER is always lagging for psi m by pi by 2. This is also always true for any harmonic, fundamental harmonic, everything. Now, when we are coming to rotor current, we have written ER by Z for a general current. Now we know that for harmonic, we are having RR and LLR. This is our Z, what I'm talking, let's say ZR. So LLR is basically, when you have nth harmonic component, this becomes N omega L, LLR, and slip becomes 1. So more or less this ZR is equivalent to N omega LLR. Say J is also there. So then for the harmonic component, the current will become slightly different. IR, let's say I call it N, and it will become ER divided by J N omega LLR. So which means for the harmonic case, IRN will lag ER by pi by 2. Everything else is same. Okay, for simplicity, you may even ignore the stator resistance and the leakage as well compared to LM. So the phasor diagram for any harmonic component can be drawn as, I will again take the flux first and towards the same direction. So if let us say this is also positive sequence, say for example, we have taken nth harmonic voltage which is having positive sequence, not all have. Sukmar, please mute. So what we will have, basically we have the nth harmonic voltage, say ESN, generating the psi mn, and then this is generating ERN, and ERN is generating IRN. Understanding my point? So this is all positive sequence. If you have negative sequence of voltages, then what will happen? Again, keeping the flux on the same line, if this is flux, now this is going in this direction. So which means your applied voltage ES will be along this direction because this psi m has to lag ES by 90 degree. So psi s will be leading this and ER will come here and current will come here. This is negative sequence. Understanding my point? How the phasor will look for harmonics? And for simplicity, what we can say that ES is almost equal to VSM. We ignore the drop compared to this magnetizing branch. So this is almost like that. Now, fundamental we have understood that this is having this phasor. Harmonic we have understood if we have positive sequence, we have this kind of phasor. If we have negative sequence, it is basically the leading lagging positions for the voltages are reversed. That is all. Correct. One is cause, another is effect. That's what you have to understand. Now tell me, which harmonics are having positive sequence in our PWM voltage when we are having the balanced three-phase system? You remember?
Fifth harmonic.
7th,
13th.
13th,
13th.
19th, all these will have positive sequence, whereas 5th, 11th, 17th, all these will have negative sequence. These will be governed by this phasor. Now, let us take only two harmonics, the most dominant ones, 5th and 7th. And let us see how the flux, let's say the 5th flux is psi m5, 7th flux is psi m7. 5th rotor current is IR5, 7th rotor current is IR7. How these are interacting with the fundamental. So fundamental flux, which is psi m1 and fundamental rotor current IR1. How these are interacting with the flux and rotor current for the fundamental. And obviously we will see what happens as a result. So interaction of flux and current we know is torque. So definitely we are talking about the quantity torque. So we will only draw these phasors, and because we are talking about the interaction about these quantities, so we will draw everything in the same phasor. So what I do, I draw, let's say psi m1 here. So this is rotating with omega s in the counterclockwise direction. Then I have psi m5, which is rotating in clockwise direction with 5 omega s. Then I have psi m7, which is rotating in counterclockwise direction with 7 omega s. There is no problem in this at all, right? No problem in this at all?
No, sir.
No, sir.
Correct. Now
Sir.
we have the current. So fundamental current is at this kind of angle. You can say this is delta. It is close to ER. So I am drawing over here IR1. And it is rotating in counterclockwise direction with omega s. Then we have 5th harmonic current, which is coming over here IR5, rotating in the clockwise direction with 5 omega s. And the 7th harmonic current IR7, which is rotating with 7 omega s in the counterclockwise direction. This is clear. All these are phasors overlapping basically. I have drawn just parallel lines. These are all overlapping. The center is same. You understand the point? Now,
Yes.
to simplify things, what we do, let us go and sit on this omega s reference frame. Let us sit on the synchronously revolving reference frame. So what will happen? Because we are sitting on the synchronous reference frame, the quantities psi m1 and IR1 will look stationary to us. So let us draw again psi m1. Now this will look like stationary quantity because we are rotating at the same speed. Then IR1 will also look like stationary with angle delta. Then we will have psi m5. What will be the speed of rotation for this?
6 omega. 6 omega.
Yes, 6 omega in the clockwise direction. And what about the 7, psi m7? Yes,
That also 6 omega, sir, but anti-clock.
6 omega, but anti-clockwise direction. This is good, right? Now we have the fifth harmonic current, which will also have 6 omega in the clockwise direction. And we have seventh harmonic current, IR7, counterclockwise with 6 omega s speed. No problem in this? Fine, right?
Yes, sir.
Okay, now this is just one instant. Let's say you have taken a photograph, and this is one instant where these phasors are looking like this. Because these are not stationary, rotating at 6 omega, next instant they will be moving. No? They must have moved to some other location. Understanding my point? So we will come to that. Now, we are trying to get torque because of interaction of all these quantities. So we can take a constant K and we can write the expression for all this. So what is the expression? Expression is psi m1 cross IR1, the cross product of these two, plus psi m1 interacting with IR5 plus psi m1 interacting with IR7. Fine? It's fine, right? Psi m1 has interacted with all three currents. Now, similarly, psi m5 will interact with IR1 plus psi m5 will interact with IR5 plus psi m5 will interact with IR7. Any problem in this?
No, sir.
Similarly, psi m7 will interact with IR1, psi m7 will interact with IR5 and psi m7 will interact with IR7. Now for the cross product, what we need to get magnitude, let's say psi m1, IR1, whatever the quantity written. The only other thing we need is the angle between these quantities, right? To get the cross product. Now, when you are checking the angle, let us take the fundamental component first. So angle between psi m1 and IR1 is delta, which is fixed. Correct? These two are not moving. This is fixed. So that's why I am saying let us draw one more instant of these quantities. So how this will look like, I will quickly draw this. You will have psi m1 still at the same position, IR1 is still at the same position, but psi m5 should have moved here because it is going in the clockwise direction with 6 omega s, and psi m7 would have moved in this position because it is going in counterclockwise direction at 6 omega s, right? So this angle will be 6 omega s t. This angle will also be 6 omega s t. Now similarly, I5 also would have moved by some angle 6 omega st in this direction, clockwise direction. And IR7 will also have moved in this direction with the speed 6 omega s. So angles are 6 omega st. And this angle is delta. Clear? Any problem in this? Fine?
Yes, sir.
Okay, so another 10 minutes and you will get the expression for torque. Now, let us solve one by one. K times of psi m1 IR1 cross product. What is the angle? And we are using the right hand thumb rule here. So we follow this. So which means we are talking about a cross product which is going inside the paper, always in this direction, right? So that's why all the angles you will see in this manner, in the counterclockwise direction, from flux to current. Fine? Okay. So what is the angle between the fundamental components, psi m1 and IR1?
Del.
Delta, right? So then it becomes sine delta. Plus, now what is the angle between psi m1 and IR5? See, it was pi, correct? Or you take like this, it was pi. Now it has moved to pi plus 6 omega t. If I draw with black color from here to here, it has moved pi plus 6 omega t, right? It is rotating with 6 omega. So after t time, the angle will become pi plus 6 omega t. So here I can write sine pi plus 6 omega t. Then psi m1 and IR 7. So what will be the angle? Again, this was pi. From here to here it was pi. Now it has reduced by 6 omega because it is rotating towards the flux. Understanding my point?
Yes, sir.
Yes, sir.
Correct. So pi minus 6 omega t it is. So here I write pi minus 6 omega t. Then psi m5 and IR1. What is the angle? See here psi m5 is here. The angle was delta. Now psi m5 has moved inside. It has now moved here to this position by 6 omega t. So angle remains delta minus 6 omega t. Correct? It is going towards the current, right?
Yes.
So the angle has reduced by amount 6 omega t from delta. Then psi m5 and IR5. What is the angle? Here it was pi, psi m5 to IR5. What is here now? Both are rotating at the same speed, so the angle remains same. And it is pi. Understanding my point? Plus psi m5 IR7. This is the third current with interacting with psi mr. So what was psi m5 and IR7? This was pi. And
So pi
now
minus 6 omega t.
again think carefully. Sampan, you jump too soon on the conclusions. 5 is rotating with 6 omega in the clockwise direction. 7 is rotating with 6 omega is in the counterclockwise direction.
12 omega.
So what it should be?
12 omega.
12 omega. So it becomes pi minus 12 omega t. Correct? Now psi m7 and IR1. What is the angle? So delta has now increased because psi m is going away from IR. So delta plus 6 omega t. Okay. So this becomes delta plus 6 omega t. Then plus psi m7 IR5. What is the angle here? Sampan? Psi m7 IR5.
Sir, pi minus 12 omega st.
Yeah, actually pi plus. Because both are moving towards and you have to see the counterclockwise direction of angle. Then we have psi m7 IR7. Both are moving at same speed, so angle remains same, sine pi. Fine. All the components we have written over here. Yes or no?
Yeah.
One of the very important derivations what you are having in this course. Fine. Now, sine pi is certainly 0. So these two components go to 0. Then you have product of two harmonic quantities over here at two places generating some component. So because this is product between two harmonic quantities, we can take this nearly 0 compared to any other quantity where you have fundamental and one harmonic. So obviously the amplitude is more. Here the amplitude is very small. Harmonic into harmonic, correct? So this we can ignore comfortably compared to any other component over here. Now we are remaining with only 4 components in this expression, or 5 components rather. This is what we are now remaining with. We have the fundamental flux interacting with the fundamental current. We have fundamental flux interacting with fifth harmonic current, fundamental flux interacting with seventh harmonic current, fifth harmonic flux interacting with fundamental current, and seventh harmonic flux interacting with fundamental current. Now, whenever two quantities which are like same harmonic, when they interact, this component is going to be DC because all these numbers are fixed. So this is our useful DC torque. This is the DC torque responsible for operating the motor, the interaction between the magnetizing flux and rotor current. You can actually work out the value of sine delta and you will reach the same expression what you have got earlier in your previous classes from the power. And then you can get the value of K, the constant as well. This will come basically in terms of poles, number of poles in the machine. So then if we remove the useful torque, whatever extra components are remaining here, this basically form what is called as the harmonic torque. So what is happening? You have one DC quantity interacting with another AC quantity, or what you can say, the sine 6 omega t, this kind of nature is basically giving a pulsating kind of waveform. So each component will look like something going like this. This is the pulsating nature or harmonic nature. We are concerned about these components. So let us take, and because all these are associated with 6 omega t, so we can say that the overall torque is basically pulsating at 6th harmonic. So we can call it 6th harmonic torque. Then tau 6 I can write after removing the DC component as some k times of psi m1. Now if you simplify here, the pi plus 6 omega t, sine pi plus 6 omega t will become minus sine 6 omega t, sine pi minus 6 omega t will become sine 6 omega t, and then delta I have told it can be very much close to 90 degree. So this can be taken as sine pi by 2 minus 6 omega t and sine pi by 2 plus 6 omega t, both becoming cos 6 omega t. So I can write the combined term IR5 minus IR7 sine 6 omega t, or I will take minus over here, plus psi m5 plus psi m7 IR1 cos 6 omega t. So these are two orthogonal components which are coming over there, right? Now we have the expression for torque. So magnitude you can write as some k times of psi m1 square IR5 minus, sorry, so yeah, IR7 this whole square plus psi m5 plus psi m7 this whole square into IR1 square. Understanding my point? So the ideal scenario for removing the sixth harmonic torque will be that you remove both the fifth and seventh harmonic voltages from the system. So there will be no fifth harmonic, seventh harmonic flux and no fifth harmonic, seventh harmonic current. This is the best scenario for tau 6 equal to 0. Now, most of the books written on basis of paper by Robertson and Hepburn in 1971, they have given that this component is little bit weak compared to this component. So simply they have ignored this other component which is associated with IR, and they have regarded tau 6 as k times of psi m1 IR5 minus IR7. Now IR5 IR7 can be written as V5 by 5, so n omega L can come, sorry, omega L can come over here, V5 by 5 and V7 by 7. So they have given the way that, okay, if you want to make tau 6 equal to 0, you only need to make V5 by 5 equal to V7 by 7. However, this story is incomplete. The other component also plays a very important role, and so this was the paper which was governing all those textbooks who are giving this kind of expression for elimination. Then you refer to paper by in 2014, and here we have got that this is not the complete thing. What we need to do, you also need to keep check on this magnitude V5 by 5, which is basically the flux component psi m5 plus psi m7. So we need to minimize this as well. Just by doing this may actually give high value of tau 6. So this is what has been given over here. So those who are interested can go and refer to that paper, and then we have the next class of optimal PWM who claim to minimize tau 6 or any in general tau n. So where tau 6 is result of V5 and V7, so tau n will be result of Vn minus 1 and Vn plus 1. Ideal scenario is you remove both the harmonics from the system, and so you will have zero value of these torque harmonics. The other scenario is that you maintain this and minimize the factor. This is another class of optimal PWM. So I stop the class over here with this derivation, and we discuss in the next class from the further sections. Any doubts up to this? Any doubts up to this?
Sir,